Hello there. In this video we're going to look at the solutions to the test that you've done recently. You're going to need a couple of things before we get going. So you're going to need the question paper and you're going to need the mark scheme, both of which I've made available. So if you haven't got them now, then pause the video and go run and get those. Question 1 is about finding the percentage uncertainty when measuring the density of a metal sphere. So density is of course the mass divided by the volume. So we need to look at the percentage uncertainty with the mass and the volume. Percentage uncertainty with the mass is 6 divided by 100. So 6 is the uncertainty and 100 is the measurement. So do 6 divided by 100 times 100, and that gives us a percentage uncertainty of 6%. Now I need to look at the percentage uncertainty with the volume. Now with the volume, we've got a uncertainty of 0.08. Divide that by the measurement, 1.6, times 100, and that gives us a percentage uncertainty of 5%. When we're dividing two measurements, then we add the percentage uncertainty. So it's 6 plus 5. So it's tempting to stop there and say that the percentage uncertainty is 11% and then put answer B as your answer. But this is there to trick you. The reason being is we've got the measurement here is the volume of the radius, and to find the volume we need to do 4 pi r cubed over 3, and that gives us our volume. So effectively we're multiplying the uncertainty here, so we need to add the percentage uncertainty here. So we've got a percentage uncertainty of 5 plus 5 plus 5, because we're using the radius 3 times. That gives us a percentage uncertainty of 15% in the measurement of the volume. We looked at 6% with the measurement of the mass earlier, and we need to combine all of them together. So it's 15 plus 6, which gives us 21. So our answer there is answer D. Question 2 was about a mass and it was being accelerated. So we got a 7 kilogram mass, and it's being accelerated upwards by 2.0 meters per second squared. And we're being asked, what's the tension in the rope? So the tension in the rope is going to be a combination of the downward force from this 7 kilograms and the upward force causing this 2 meters per second squared acceleration. So let's first of all look at the force from the downwards from the mass. So that we would just simply do 7 times 9.81 to find its weight, which is 68.67 newtons. And that's one of our answers. And again, that's there to trick you. We also need to add the force causing this acceleration. And it's this acceleration, or the force that's causing this acceleration, is accelerating this mass. So we need to go force is equal to mass times acceleration. Rearrange it to find, or it's already rearranged to find the force. So we need to do the mass, which is 7, times 2, which is 14. The tension in the string is going to be the resultant of these two. If we add those together, then we get 82.67 newtons, which is answer D. Question 3 is about floating, and this one has got 3 options, 1, 2 and 3, and we need to say which ones are true. So let's check each statement and then decide which of these is going to be the case. So choice number 1 is that the net force acting on the cork is equal to the weight of the water displaced. Now, if that was true, then we would have the net force would be equal to just the weight. So we're looking at the net force is equal to the weight. That would mean that there's only one downward force, which would mean that it would be accelerating downwards, which isn't true because it's floating. Option 2, the weight of the cork is equal to the weight of the upthrust. So that's saying that the downward force from the weight is equal to the upward force of the upthrust, which is true because when they're equal, it means that the resultant force is 0, or the net force is 0, and it wouldn't be moving, or it wouldn't be accelerating, which is obviously the case. Option 3 is the upthrust of the cork is equal to the mass of the water displaced. Now that's nearly true. If this word here was the weight, then it would be true. But here it's talking about the mass. So the weight, so the upthrust of the cork is a force, and this is comparing it to the mass, which we can't do. So we've got here that our only one that we've got is answer 2, which is answer D. Question number 4 is about Hooke's law, and we've mainly done Hooke's law in terms of stretching springs, but it can also work for compressing springs. So what we need to do here is use the force is the spring constant times the extension. So here we've got an extension of 1 centimetre, and we've got a force of 200 newtons. And we're being asked what is the spring constant. So if we rearrange to find the spring constant, the force divided by the extension. So the force, 200 newtons, and we need to be careful here with converting the units, because we've got 1 centimetre, which is 0.01 metres. That gives us an answer of 20,000. 20,000 is, or this answer here, is the same as 20,000, so our answer there is answer C. Let's take a look at this one. This one involves a balloon, and the balloon is travelling vertically downwards with a constant acceleration. So it's accelerating downwards. This must tell us that there is an overall force, or the resultant force, in a downwards direction. So let's have a look at the forces that could cause that downward force, and let's see if it matches any of these. So the upthrust of the balloon is U. So there's going to be an upward force U. Its weight is going to be downwards, and we've got an air resistance. Now we've got to think carefully about which direction air resistance is exerting. It's accelerating downwards, so the air resistance is going to be exerted upwards. So we're looking for an overall downward force, and here the force is the overall downward force, not the air resistance, so just to make that clear. So we need an overall downward force. For that to happen, the weight needs to be greater than the resultant of the upthrust and the air resistance. And that is answer D. In question 6, we're being asked about the mass of we're talking about a brick, and we're talking about the pressure that that brick is exerting on the on a table. So let's just quickly sketch a rough sketch of a brick, and we're told something about the dimensions here. So we know that the dimensions have been labelled, or the length, the width and the depth have been labelled A, B and C. And we know that A is less than B, which is less than C. So we know that A is the smallest here. So that side there must be A. We know that B is less than C. So this side here must be B, and the long side must be C. The brick is placed on a table such that the pressure it exerts on the table is at a maximum. Now remember, pressure is equal to the force divided by area. So to make the pressure a maximum, we need the smallest area possible. And this bit here is the smallest area. Now that area is B multiplied by A. So our area here is B multiplied by A. The force here is the weight of the brick. So our force here is the mass times the acceleration due to gravity. So we need the force divided by the area, so mg over BA or AB, whichever way you like, and that gives us our pressure. And that matches up with answer A. In question 7, we're being asked about two balls, X and Y, that are dropped from a very tall building. And we know that X has got a greater mass than Y. So here's X and here's Y, and they've just been dropped from a very tall building. Something that we should be able to work out is that the downward force, so in other words the weight of X, is going to be larger than the weight of Y. So let's check that whether the first statement is correct. So the balls hit the ground at the same time. That one's not true, even though we should know that the acceleration due to gravity is the same for all objects. We're told that they reach terminal velocity. So that means we need to take into account air resistance. We should know that air resistance, or drag force, increases with velocity. So as velocity increases, drag increases. So if that's the case, then even though they're accelerating at the same rate initially, X will need to reach a larger velocity to equal out that weight to reach terminal velocity. Y, on the other hand, will need a smaller drag force to overcome this weight to reach terminal velocity, and this lower drag force requires a lower speed. So it'll have a lower terminal velocity, and so that will mean that X will hit the ground first. So where it says the balls will hit the ground at the same time, we know that that's not true. The terminal velocity of Y is greater than that of X, and so we know that that one's not true because we said that the terminal velocity of X will be greater because it needs to reach a greater velocity to overcome or to balance out the downwards weight with the drag force. C, the initial acceleration of the balls is the same. Now that one is true. The initial acceleration is going to be equal to 9.81. So at the moment that the balls are dropped, the acceleration is going to be 9.81 meters per second squared. The balls have the same kinetic energy just before hitting the ground, and that one isn't necessarily true because X is going to have a greater mass and it's going to have a greater terminal velocity. So when it hits the ground, it's going to have more kinetic energy because the kinetic energy is half mv squared. So if the mass is greater and the velocity is greater, then that kinetic energy is going to be greater. So here, our answer is C. Question 8 is about a small electric motor that's got 20% efficiency. This is its power output, and it's lifting a mass of half a kilogram. Something that we should do immediately is take into account this 20% efficiency. So that means that only 20% of the power being used per second here is being done in a useful way. So first thing that we need to do is find 20% of 9.6. And that gives us 1.92 watts. So this is the effective power of our motor. Now to decide what the velocity is, so we're probably not used to dealing with these sorts of questions, but I'll talk you through how you can do it. So the way that we can do it is start off by looking at the power. Now the power is the work done per unit time. And the work done is equal to the force times the distance in the direction of that force. So distance travelled in the direction of force. So if we don't turn this into the power by dividing by time and do the same over here. So this term here is equal to the power, and that's equal to this. Now what we've got in here, we've got a distance divided by time, which tells us the speed. So we can substitute d over t here for the speed. So I'm going to use the symbol v for velocity. So what we have, so let's change this back to power. So power is the force times the velocity. So here, what have we got? We've got the power, and we've got the, well, we haven't got the force, but we can find the force because the force is the mass times the acceleration due to gravity. So if we rearrange it for velocity, then we have the power divided by the mass times the acceleration due to gravity. Power is 1.92 and the mass is 0.5. Acceleration due to gravity 9.81. That gives us an answer of 0.39 meters per second, which is answer A. Question 9 is about a car that accelerates uniformly from rest, and we're told that air resistance are negligible, so you don't need to worry about any drag forces, and the car travels at 12 meters in the second of its journey. So how far does it travel in the fourth second? Now this is a really tricky question, and the way that I went about solving it was to sketch out a velocity time graph. So here we've got the velocity against the time, and let's break it up into seconds. So this is the first second, third second, and then this is the fourth second, and we're told that because it's accelerating uniformly, it's going to be a straight line. And we're told that in the second, so this portion here, it travels 12 meters, because remember the area under the graph of a velocity time graph tells us the distance traveled. So in the second it goes 12 meters. We can also look at the symmetry of this graph as well to help us solve this. So we break this up into extra sections. So breaking this up even more, we can look at some patterns that emerge in this graph. So this shape here, so all these little triangles that I'm labeling in red are all equal size. So what I did is I went about saying that, well, I just called this A, and because that part of the triangle there is A, this part of the triangle there must be A, and this part here must be A. So I'm going to just switch to blue this time. So we've got a trapezium here of sides, so one parallel side is A, and then the other parallel side is 2A. Now the area for a trapezium is A plus B. This is the general formula for it. A plus B divided by 2 times the height, and here this is our height. So our area for our trapezium here is A, because that's one of the sides, plus, well, in B here is going to be 2A, divided by 2. And then our h is going to be 1, so times 1. And that gives us 3a over 2. So we know that, and that area is equal to 12. So 12 equals 3a over 2. So we can work out what a is. So let's do that. So cancelling out that 2. And then that tells us that a is equal to 8. So we know that this distance there is 8. Or in other words, 8 meters per second. So let's take a look at what's happening in the 4th second. So in the 4th second, let's go back to that red pen. So let's put a few more guidelines on here. And here we've got A, and A. So in the 4th second here, one of the parts, and what we're trying to do here is find the area underneath the graph in the 4th second. And so that's 3a on one side and 4a on the other side. So the area under our graph for the 4th second is going to be 3a plus 4a divided by 2 times 1. Now remember, a is 8, so that'd be 3 times 8 plus 4 times 8 over 2. So that's going to be 7, so effectively 7 times 8, which is 56, divided by 2, which is 28, which is answer A. In this question, we're being asked about errors that might be occurring in a measurement, and something that we need to do is just study the diagram for a moment. So at the moment, we've got something wrong here. So we're measuring the length of this section of wire, and can we see that it doesn't start at the 0 point on the measurement? So assuming these are, let's for argument's sake say they're centimeters, we're going to be 1 centimeter. We're going to be 1 centimeter larger than we actually think here, and that's just from this error going on here. We've also got a parallax error here, so I think the true value is somewhere about here, but where the eye is looking, we're getting an error here. Now we need to think about what kinds of error these are, and we've got some, so these are systematic errors. These are errors with the system that's being used to take these measurements. So there's a problem with the system here and a problem with the system here. This eye should ideally be in the line of sight, looking down there. So here we've got some systematic errors. So let's check these answers and then see which one best fits. So there are random errors but no systematic errors. So we said there were systematic errors, so that one's not true. There are systematic errors but no random errors. So this one could be true. So let's put a question mark at it at the moment because it has got systematic errors. There are both systematic errors and random errors. So this could be true because there are systematic errors. There is no overall error because the random errors and systematic errors cancel out. So we'll check that in just a moment. So we've talked about systematic errors and we've ruled out answer A. Let's have a look at those random errors. So random errors are errors that you get from a measurement that are from things that you can't control. So for example, the length of this wire here is going to be changing due to temperature, due to thermal expansion. It's going to be changing from all sorts of other small effects. So even something like gravitational waves will cause the space that the wire's sitting in to either expand or contract. So even they're going to be random errors. So they may be small, but they're still errors. So random errors are things that are beyond our control. And it doesn't say anything in the question about their all other factors being controlled. So we know that there are random errors. So let's check check those answers again. So it could have been A because there are random errors, but we've decided there's no systematic errors. There are systematic errors, but no random errors. So we know that one's not true because there are random errors. There are both systematic errors and random errors. Well, that one is true. And there is no overall error because the random errors and systematic errors cancel out. And that one's not true because you'll never get the random errors and the systematic errors to be absolutely the same value. So we know that this answer is answer C. Question 11 is about the nature of photons, and we're given 3 options, and we need to say which ones are true. So let's look at these different statements. So the speed of a photon changes at the boundary between air and glass. So you've probably done an experiment where, so this is a rectangular glass block, and you might have seen a light ray coming in and then changing direction like that, and then changing direction again. The cause of that change in direction is due to a change in speed of the light as it passes through the air. So here we've got the air and here we've got the glass. And because of the materials that they're made from causes the speed of the photon to change. So option A here, or option 1, or statement 1 I guess, is the speed of the photon changes at the boundary. Well, that's true. Photons are electrically neutral, so that one's true as well. There's no positive or negative charge on photons, and the energy of a photon depends on its wavelength, and that one's true as well, because we know that the energy of a photon is hf, so Planck's constant times the frequency, and frequency is the velocity of a wave divided by its wavelength. So E equals h v over lambda, although we might sometimes use hc. In fact, let's use hc over lambda, where c is the speed of light, because we're talking about photons of light rather than any other kind of wave. So we know that all of these are true, so statements 1, 2, 3 are correct, which is answer A. Question 12 shows the displacement time graph for a particle as a progressive wave moves through a medium. And we're being asked, at what point is there a phase difference of 180 degrees? So we're looking at this point and we're looking for a phase difference of 180 degrees. So 180 degrees away is half a wavelength. So this is let's draw a line here to indicate where this wave is starting. So 180 degrees is half a wavelength, so that's C. So that's half a wavelength here. And let's just check. So this is one wavelength, so this dotted red line here is one wavelength, which is 360 degrees, and our line here is about halfway in between. So we know that this one is answer C. Question 13 is another question to do with waves. It's to do with the refraction of waves. And we've got an incident ray, and it is refracting at a boundary between two media there. So something that we should be able to note here is that this could represent something like a light ray going from, say, glass into air. Now we know that that's the case if we sketch out a so this is our rectangular glass prism that we might have done experiments with, and we got our incoming ray here. Then it's going to refract towards the normal as it goes from the air to the glass and away from the normal here. So what we're looking at here, so this diagram here, is looking at this interaction that's going on here. So let's check through the statements and then decide which of those statements is correct, and then pick an option. So the refracted light ray and incident light have the same wavelength. So that's not obvious from the diagram, but if we have a quick look at this animation, so we look at this animation, then we can see that when the light ray goes from the glass to the air, which is what we're looking at, then the wavelength it increases. So the wave speeds up, and the wavelength increases. So where it says the reflected light and the incident light have the same wavelength, we know that's false. The speed of the light in medium 2 is greater than that of the speed of the light in medium 1. Well, that one is true, because as the light travels from glass to air, it's traveling faster. The angle of incidence is the critical angle. Now that one's not true, because if this was the critical angle, then our light ray would be coming in here, and the critical angle is the angle at which all light is reflected. Now we've got some reflection here and some refraction. If that was the critical angle, then our light ray would be, the refracted light would be travelling along this path here. And that's not the case, so we know that's not the critical angle. So only 2 is true here, and that's one of our options. So this one, answer D we were looking for. Question 14 is about electricity. So a resistor is connected to a power supply, which is correct about the conduction electrons in the resistance. They travel at the speed of light between collisions with ions. So something that we should note is that the electrons within a wire don't travel at the speed of light. They make random collisions with vibrating electrons. So the electrons that are moving through the material, they're not colliding with vibrating electrons. They travel at their mean drift velocity between collisions. So that one's not true. I'll just explain why. We've got so here we've got a wire here, and let's put a few, so those little dots are supposed to represent the atomic nuclei that make up the wire. They might be copper atoms, nuclei of copper atoms, and here's our electron here. So it starts up its journey, and then it might interact with some of these copper atoms. So it might make a path something like this as it's travelling through. Sometimes it might bounce off and go backwards, but it's going to make some kind of path like this. Now between each collision, it's going to, so in between each collision, there's going to be a period of acceleration. So when we're talking about the mean drift velocity, we're talking about the overall. So we're talking about overall distance that our electron has travelled, divided by the time that's taken. So they travel at their mean velocity between collisions is not true. They drift towards the positive end of the power supply, and that's something that we should know about electrons. If we've got a electric circuit, so sketch a quick little, and it's about a resistor. So this big part is positive, small part is negative. We know that the electrons will be repelled from the negative end and attracted to the positive end, so that we know that D is the answer that we're looking for there. Question 15 is about a filament lamp. It's connected to a voltage of 120 and the lamp has got a power of 60 watts. Lamp is connected to a power supply so that it lights normally. And we need to check which of these statements is true. Charge passing through the filament in 1 second is 2 coulombs. So 2 coulombs in 1 second, so that is going to be equal to 2 amps. So remember the current is the charge divided by the time, and for statement A, the charge is 2 coulombs, time is 1 second, so that would be a current of 2 amps. We can check that by saying that the current is the power divided by the voltage, so that would be 60 divided by 120, which is 0.5. So our current with this lamp is 0.5, and statement A is saying that the current should be 2. So we know that that one is false. The lamp transfers 60 joules for each coulomb passing through the filament. Now when you hear about joules per coulomb or joules for each coulomb, we're talking about the voltage. So the voltage is the energy per unit charge. So the energy per unit charge. And this is saying that 60 joules for each coulomb. So we're saying that's 60 joules for every 1 coulomb. So that's statement B is saying that the voltage is 60 volts, which isn't true because we're told that it's 120. The lamp transfers 120 joules in 2 seconds. So joules per second is the same as the power. So power is the energy transferred per unit time. And this is saying that we've got 120 joules in 2 seconds, which is equal to 60. So our power, so this is saying our power should be 60 watts, which is true. Question 16 is another electricity question. So it's about a battery, and it's got an EMF of this and an internal resistance of 2.5 ohms. So let's first sketch out what we've got here. So here's our battery, and this is the internal resistance. Typical way that you'll see it represented is with the symbol for the battery here. This is the internal resistance, and you'll often see it with a little dotted line around it. And it's connected to an external resistor. So here's our external resistor. And the current in the resistor is 350 milliamps. Something that we can add here is that because it's a series circuit, the current everywhere is going to be 350 milliamps. And we want to know what is the power dissipated by the external resistor. So we want to find what is the power in this part of our circuit here. Now to do that, we need to find what the resistance is. So let's find the resistance of this external resistor. Something that we should know when we've been studying internal resistance is that the EMF of the cell is equal to the current in the circuit times the external resistance plus the internal resistance. So here we can rearrange for the external resistance, and so we take the EMF divided by the current and then take away the internal resistance. When we do this, we have EMF was 8 volts divided by the current, 350, and it's milliamps, so we need to times 10 to the negative 3 minus 2.5. And that gives us an answer of 20.4 ohms. So we know that our resistance here is 20.4 ohms. But we're being asked what the power is. And something that we should know is that the power is I squared R. So the current squared times the resistance. And so when we do I squared R, so we go I squared, and remember times 10 to the negative 3 again, because it's milliamps, and then that is all squared, times our resistance, and that gives us an answer of 2.499 to two significant figures, 2.5 watts, which is answer B. Question 17, we're being asked to show, find the wavelength of a sound wave, and then the data that we're given is a displacement time graph of an air particle as a sound wave passes. So this is we've got an air particle that's vibrating up and down, and this is how its position, this graph shows the position that it's changing with as time progresses. And we're being asked what the wavelength is. Now, we're told what the speed is, and it's tempting to look at this graph and then just measure the wavelength like that and say, well, the wavelength is that. But this isn't the actual wave, this is the position of a particle that's transferring the energy. And so it's tempting to say that, well, the wavelength is 2, but that's not the case. What we can do, though, is we can find the period of the wave. So the period of the wave is from is the time taken for one complete wave, and we've got time axis here. So 0, so one whole wave is equal to 2 milliseconds. That's 2 times 10 to the negative 3 seconds. We should know that the frequency of a wave is 1 over the time period, and 1 over the time period here gives us 0.5 times 10 to the 3. So this is our frequency. We can then use the speed of sound that we're given, because the speed of a wave, or velocity of the wave, is the frequency, or the velocity of the wave divided by the frequency tells us the wavelength. So we can say that the speed, 340, divided by the frequency, but the answer that we're looking for is answer A. Question 18, another question about internal resistance, and which of these is true about increasing the terminal potential difference. Now remember, the terminal potential difference is what we would get if we measured the voltage across that. So let's check each of these statements. Increasing the EMF of the cell will increase the terminal potential difference. Yes, it will. If we increase say this here is the EMF, so potential difference across there, or the voltage across there is the EMF. Increasing that will increase the voltage here. Increasing the value of the external resistance. If we increase the value of the external resistance, then that will increase the value of the terminal potential difference as well. And increasing the value of the internal resistance, so if we increase the value of the internal resistance, then these lost volts will increase. So we'll get a larger lost volts here, so that will mean a smaller terminal potential difference. So we know that one's not true, so it's answer B. This question shows a transverse progressive wave, and it's travelling from left to right along a string. Horizontal line shows where the string is when there's no wave present. Which direction is the string at point P moving at the instant shown? So to answer this one, I'm just going to sketch where this wave will be a short time after this instant that we're showing here. So the wave is moving from left to right, so each point on the wave will be slightly further to the right. So if we sketch that in, then what we found is that point P, because P is not only moving because it's a transverse wave, P is moving up and down and transferring the energy to the right. So P at that point is moving downwards, because in the next instant it's going to be here, because the wave would have moved to the right. So at the moment P is moving downwards, which is answer B. This question is about a semiconductor diode, and we're given the current and voltage characteristic of our semiconductor diode. And we're given some statements we need to decide which is true. So the resistance of the diode can be, which statements about the resistance can be reduced from the characteristics? So is the resistance 0 between 0 and 0.7 volts? So 0.7 volts is there on our graph, and we're being asked, is the resistance 0 then? Now if the resistance was 0, then you would have a current would easily be able to flow, and we're increasing the potential difference, yet no current is flowing. So instead of the resistance being 0, here the resistance is effectively infinite, or not necessarily infinite, but very, very large. So we know that that one's not true. It is constant between 1 and 1.5. And it's tempting to say that the resistance is constant because there's a straight line graph there, straight line on the graph. But the resistance is only constant when it goes through the origin. So when your straight line graph doesn't go through the origin, then it shows that it's not a constant resistance. So it is constant between there and there. That's not true. The resistance is 0.4 ohms at 1.2 volts. So hopefully 1.2 volts. If we read up, whoops, it's not quite 1.2. Misread the scale there. 1.2. Oh no, that is 1.2. Let's read up here and across, and well, it's tempting to do that, but this of course is measuring the current, so that one's not true. So that only leaves answer D, which is saying that the resistance decreases, and because the gradient is increasing, we know that the resistance must be decreasing. So our answer here is answer D. So now we're going to take a look at the questions that involves you giving an open response rather than a multiple choice answer. And we're going to focus on the questions that we found particularly difficult. So most of these you can go through by yourself, but we'll focus on the ones that are the most difficult. So question 1, we're told that speed is a scalar and velocity is a vector, and we need to state one difference and one similarity between speed and velocity. So a difference could be that a vector has direction and speed does not, or we could say that the scalar does not have direction. A similarity, we've got a couple of options that we could have chosen there. So we could have said that they both have the same unit, or we could have stated the units meters per second, or we could have said that they both have magnitudes. There's a couple of answers that we could have given there. If we take a look at this next part, then we're provided with a diagram, and we're told there's this toy locomotive, which is another word for a train, and it's moving around this circular track, and we are asked to calculate its speed. And to calculate the speed, we simply do that the speed is the distance divided by the time. Distance here is the circumference of the circle, so it's twice the radius, so 2 times the radius times by pi, and the time we're told was 12 seconds, and that should give us an answer of 0.31. In this next part, we have to calculate the magnitude of the displacement after it's moved a quarter of the way around the track. Now, a few of us struggled with this, so I'm just going to annotate the image that we were given just to demonstrate what we needed to do for that. So if we take our starting point here and a quarter of the way around the track, I've indicated by this blue line here. And we need to find the displacement that the toy locomotive has undergone from here to here. And the displacement is the straight line distance. So it's not this curved distance here, it's this straight line distance here. And we should notice that this, because it's a quarter of the way around the track, this makes a right angled triangle with 0.6 and 0.6 as its sides. So we can simply use Pythagoras' theorem and say 0.6 squared plus 0.6 squared is square rooted, is that distance or that displacement, which should give us 0.85 meters. So that was just one that a few of us found a little bit tricky. Next up, we needed to explain why the displacement was 0 after time t equals 12 seconds. So after time t seconds, or after time 12 seconds, the displacement is 0. So in other words, it's gone back to its original starting position. If the displacement is 0, then the velocity must be 0 as well, because displacement divided by time is velocity, and displacement 0 divided by 12, which can be 0. Also need to explain why the locomotive changes even though the speed is constant, and for that we need to explain that the direction constantly changes. So whenever direction changes, velocity changes as well. Let's have a look at question 2 now. And question 2, we need to state how the magnitude of the drag force affects its speed, and we needed to say that as speed increases, drag force increases. If we want to get into a little bit more detail, then we could have said that the drag is proportional to the speed squared. Next up, we need to describe an experiment Galileo carried out which overturned Aristotle's ideas of motion. Now there's 3 marks available for this, and the first mark we get for describing an experiment. So we could have said something along the lines of Galileo took some objects of different masses but the same size and shape, and dropped them from the Leaning Tower of Pisa, for example, and that's a description of a experiment they did. We could have also described an experiment like rolling balls of different masses down a ramp, and then so the idea of dropping objects of different masses and seeing what happens. Second marking point is the observations. So we need to describe the observations that Galileo made, and the observations would have been that the balls hit the ground at the same time, or the balls reach the bottom of the ramp at the same time. For our third marking point, we need to explain what the results of this told us about motion and how it overturned what Aristotle thought about motion. So objects landing at the ground at the same time indicates that their rate of acceleration is independent of mass. So in other words, all objects fall with the same acceleration. But we also needed to say that what Aristotle thought, and we need to say that Aristotle thought that heavier objects fall faster. Let's take a look at part C now. Part C is about a skydiver, and we need to state the two forces acting on the skydiver when they reach terminal velocity, and the two main forces are the weight and the drag, or we could have said weight and air resistance. If we have used the word gravity instead of weight, then we haven't got the mark, because gravity is something that causes a mass to have weight. So we can't say that gravity is a force, because it's the weight that is the force. If we take a look at this next one, so there's 4 marks available for this, and to get those 4 marks we need to both describe and explain how the magnitude of the deceleration changes. So we need to describe what's happening and then explain what's happening. So if we take a look at our mark scheme, the first 2 points are given for the explanation. So the parachute opens and the drag force increases. That's our first marking point. Second marking point is the drag decreases as speed decreases. So that explains why the deceleration changes. So we've looked at our explanation, and that is for the first and second marking point. The third and fourth marking point describe how the magnitude of the deceleration changes. So the magnitude of deceleration decreases between 50 meters per second and 4 meters per second. So if we're saying something about the magnitude of the deceleration decreasing, then we're describing it, and we also need to then explain what the deceleration is like at terminal velocity. So we need to say that deceleration is 0 when it's reached terminal velocity. Let's have a look at question number 3 now. State the principle of conservation of energy, and that's a fairly straightforward one. We need to just say that the energy can neither be created nor destroyed. I've shown my working for calculating the loss of gravitational potential energy in the next one. This next question is a SUVAC question. So we need to explain that when the glider starts from rest, show that it has a particular velocity. And it's a SUVAT equation, so always start your SUVAT equations by writing down what you know. So that's what I've done here. I then realised I needed to use v squared equals u squared plus 2as, and then when you work out v squared there, then it should be 1.8 meters per second. Next up, we're calculating the kinetic energy of the glider, and not to be confused with the kinetic energy of the mass there. So we're talking about the glider. So we've got to make sure we use the right mass there. So we do the half 0.5 times the mass times the velocity squared. We're told what the velocity is, and that's our answer here. Next up, we need to explain why our answers might be different. So the gravitational potential energy of the mass that we worked out, that was 0.59 joules. We've just worked out that the kinetic energy of the glider is 0.41 joules, and we're asked, well, how come they're different? It's tempting to say that it's due to friction, that frictional forces slow it down, or something along those lines. Air resistance we might have talked about, but if we've written that, then we haven't got the mark. The reason being is because in the question it states that it's on a horizontal frictionless track. So we can't call into play friction here. But what we should notice is that when we raise this 0.1 kilogram mass, it's got some gravitational potential energy. When we let go of it, it causes the glider to move this way, but it also causes itself to move this way. So if we take a look at our mark scheme, for that question, it says the kinetic energy of the 0.1 kilogram mass has not been taken into consideration. So we've calculated the kinetic energy here, but we haven't taken into account this kinetic energy. So that's where that missing kinetic energy is. The next question is about waves, and we need to explain the difference explain the meaning of interference. So there's 2 marks available there. So we needed to explain the idea that interference means that at a point in space, 2 waves meet or interact or superpose, we might have said, or combine. Some idea that it's 2 waves meeting, and that the result of that is a change in the intensity or a change in the amplitude of the wave. So first mark is for pretty much saying that waves meet, and second mark is for talking about how their displacement combines. Next question, we need to explain what coherence is, and coherence is the idea that there's a constant phase difference between waves. So just to sketch it out, here's a wave here, and make a coherent wave here, and not precise because I'm just drawing this freehand, but it's the idea that all the peaks and all the troughs line up perfectly along the whole wave. So this is what we mean by coherent. Let's sketch a quick wave that is not coherent, and I guess that could be any other wave other than the one that we've just drawn. So there's just a random wave that I've drawn just freehand there, and although the peaks are kind of lining up there, we've got a peak and a trough meeting here, peak and trough meeting here, and then it's all over the place. There's no pattern between these 2 waves. So that's what coherent means. This question is about interference, and for this one we need to use the equation lambda equals ax over d. And when we're using this, lambda is obviously the wavelength of the wave. A is the slit separation. So when we're talking about a young slit experiment, we're talking about the slit separation. In this case, we are talking about the distance between the 2 microwave transmitters. X is the fringe separation. So you have your light and dark fringes on the screen over here. Well, that's what we'd have if it was light, for example. Here we've got levels of high intensity and low intensity, and it's the different distance between those maxima is X, and then the distance to where we're measuring is big D there. So to solve this problem, we're being asked, or actually just explaining part I as well. So we'll go back to part I in just a moment. But what we're being asked, we're asked what the separation is. So let's find out what that separation is. Well, separation between those maxima is going to be X, so we need to rearrange for X, and X is lambda D over A, which we should be able to work out as 0.75. A couple of mistakes that people made was when we were giving the wavelength. So a few people used 30, but of course the wavelength is 30 millimeters, and we need to make this in meters. So we should have done 30 times 10 to the negative 3, or we could have written 0.03 meters. So a couple of people slipped up on converting that wavelength there. So let's go back to part I, and we need to use the ideas of path difference or phase difference to explain how the interference pattern is formed. And to do this, we're just going to sketch a couple of lines on here. And so you've got one line there and one line there. And let's just call this one B because it's coming from B, and let's just call this one A because it's coming from A. And the line is showing the path of the waves, the microwaves, from B to point P. And this line is showing the waves from point A to point P. And we can see that line B is longer than line A. So there's a path difference there. The path that they've taken is different. But so but we need to talk about that in terms of the wavelength. So let's talk about that path difference. So we needed to say that if the path difference was n lambda in length, then we would have maximum intensity, or it would produce constructive interference, and that would be where we get maximum intensity. So we get one mark for saying that the path difference is n lambda, and another for saying that the maximum that causes maximum intensity. Let's have a look at what happens when the path difference is different and they're out of phase. So let's just go for a different color here. Let's go for a red line here. And we're going to look to see where they're out of phase now. So out of phase here is going to be somewhere in between those points of maxima there. And in this case, the line that I'm highlighting here, it's gone further, but because there's destructive interference, it hasn't gone n lambda further. It's gone 2n plus 1 times lambda over 2 longer. Another way of saying that is 2 is n lambda plus a half. That would have got us another mark there, and we needed to say that that would have caused destructive interference there. So as long as we got 3 of those points, then we would have got those 3 marks. State the effect, if any, on the position and intensity as the following are changed. So we're first going to look at the amplitude of the transmitted waves is doubled. The separation of the transmitters is halved, and then the phase is reversed. This simulation here is showing 2 wave sources and the interference pattern that they produce. So these can be, this is one of our microwave transmitters, and then this is another, and then this is representing the interference pattern that it's producing. And we're being asked to comment on the position and the intensity of the maxima under various changes. First change that we need to look at, number 1, is if the amplitude of the transmitted waves is doubled. So we're going to simulate that by increasing the brightness on our controls here. And I want you to pay close attention to how the position and the intensity of those maxima change. First of all, the position. When we increase the brightness, the position of those maxima remain unchanged. So they're following the same path. And when we turn the amplitude down, then they're still following those same paths. What we should know is that when we increase the amplitude, the intensity of those maxima increases, but to get the mark we need to say how much they're increasing by. And something that we should know is that the amplitude squared is proportional to the intensity of a wave. So if we double the amplitude of a wave, then it quadruples the intensity. So to get the full mark we need to say not only that the intensity increases, but that how much the intensity increases by, which is a factor of 4. For part 2, we need to explain how the separation of the transmitters, if that's halved, then how that affects the position and intensity of those maxima. So we're going to halve the separation by moving them closer together, and pay a close attention to how those positions of those maxima change. And what we should find is that the maxima become separated by a larger amount, so the positions have increased. But to get the full mark we need to say how much they've increased by, and we should know that the separation of the maxima and the separation of the wave sources are inversely proportional to one another. So if we halve the separation of the wave sources, then the position of the maxima doubles. So that's our first mark, and we need a second, and our second mark was for explaining that the intensity remains unchanged. So if we look at the intensity down here, then we'll notice that that remains unchanged. So let's move it back to its original position and concentrate on down here. We should get the same intensity of waves. In the third part, we need to say how the intensity and the position changes when the phase of transmitter A is reversed. So we're going to change the phase difference using our controls down here. And at the moment, we've got a maximum that is running straight down the middle of the screen. And if we put them so that one of them is out of phase, then we've now got a minimum running down the center and maxima where there once were minima. So our answer to that question is in terms of the position and intensity. When we're talking about the intensity remains unchanged. Those waves are no more or less intense, but in terms of the position, where there were maxima, we've now got minima, and where there were minima, we've now got maxima. The final question, question 5, was about a 12-volt lamp, and it had a power of 36 watts, and it's lit to normal brightness. We've got a negligible internal resistance, so we don't need to worry about that. And the lamp is switched on for 1 hour, and then we're told that that's 3,600 seconds for a time of 1 hour, and calculate the energy supplied. And we should know that energy supplied is the power times the time. So the energy, or the power, was 336, and times that by the time. Remember, we need a time in seconds, and that should give us an answer of 129,600. Second part of this question, we needed to work out the charge flowing through this. Now there's two ways that we could have gone about doing it. Either way is perfectly fine. Quickest way is to say that is to remember that the voltage is the energy transferred per unit charge. Rearrange that for the charge. So it's the energy divided by the voltage. Energy we calculated in the last question, which was 129,600, and divided that by the voltage, which was 12, and that should give us 10,800. And we're asked for the unit as well, which is coulombs. That's method 1. We could have also done it slightly longer way, and we could have said that the charge is the current times the time. Not given the current, but we've got what we need to work it out, because the current is the power divided by the voltage, which was 36 divided by 12, which is 3. And then we could say that, so now we've got the current, so we could say that 3 times whatever the time was, 3600, gives us our charge, which again is 10,800. So 2 ways to go about that one. Second method slightly longer, but still perfectly valid. Total number of electrons passing through the lamp is next up, and whenever we are asked the number of electrons, so let's just have a quick little recap, because this is something that we find difficult. Number of electrons is equal to the charge divided by the charge of one electron. So for this particular question our charge was 10,800, and we're dividing by the charge of the electron, which is of course 1.6 times 10 to the negative 19, and that should give us an answer of 6.7 times 10 to the 22. For this next question, we need to describe what's meant by the mean drift velocity of electrons in a wire, and to gain those marks, we need to talk about the idea that it's the average displacement. so along the wire per second. So average displacement along the wire, not necessarily the average displacement in terms of the actual path the electron has taken. So I'll just sketch what I mean by that. So this is going to be our wire, and we're going to just sketch in some, so these are supposed to represent the atomic nuclei. So say it's a copper wire, these are representing the nuclei of the copper atoms. And here's our electron, and the path of an electron through a copper wire, it might be something like this, where it's interacting with some of the copper nuclei. Sometimes it's travelling backwards through the wire, just by these random collisions. And the mean drift velocity isn't to do with each section of its journey, it's to do with the average overall velocity. So its displacement from, say, its starting point here to its end point here. So we need to talk about that displacement divided by the time that it took to get there, and that gives us our mean drift velocity. So that's our first marking point. We need to talk about the idea that it's the average displacement. We could have also said that they slowly move in one direction through the metal. Now that's slowly moving over time. So we've got this zigzaggy path that the electron is actually making, but over time it will make progress through the wire. So that's something that we could have said for our second marking point. For our third marking point, we needed to say that they're constantly colliding with the nuclei that make up the wire. So it's quite tricky to get those two marked, because I think it was a bit of a sneaky mark scheme, but hopefully we got a couple of those marks. And if you're not sure what to do with a question like this, then just give the definition for mean drift velocity, and that's something that we should be learning using flashcards, for example. Final question was about calculating the mean drift velocity in the wire, and then we should know that the mean drift velocity is the current divided by the number density, so the number of charge carriers, times the cross-sectional area times the charge of those charge carriers. Let's take a look at the data that we're given in the question. So we've got the number of free electrons there, so that's our n. We've got the cross-sectional area there. We should know the charge of the electron. And are we given a current? Yes, we are. Here's our current here. So we've got everything we need to do that. So it would just be 3 divided by the number of electrons, which was 8 times 10 to the 28, times that by cross-sectional area, 1.1, times 10 to the negative 7, times the charge of the electron, 1.6 times 10 to the negative 19. That should give us a mean drift velocity of 0.0021 meters per second, which is pretty consistent with the mean drift velocity of an electron through a wire. So whenever you're asked to calculate a mean drift velocity, you're going to get quite a small number, quite a small velocity. It'll be millimeters per second. I hope you found this video useful, and by all means come and see me if you need any further clarification on any of the answers that I've given. And thanks for watching. I'll see you in the next one.